This is our lecture number 3 regarding Introduction to GIS, and we continue our discussion about hardware and software. This is the table of contents for lecture 3. We're going to look at hardware considerations, and under the hardware considerations, look at different aspects. All GIS are not alike. GIS is not a turnkey system. Building a database is the largest initial expense. Building your database is an ongoing process. Your database is the most valuable asset. We're going to look at all of these aspects when you're looking at implementing a GIS. The next topic is how are information systems created. And then lastly, we're going to look at system architectures. These are the implementation architectures that we can implement a GIS. There are 3 types: independent functional processes. We can have a mainframe or central approach, or we can have a network distributed processing environment. Hardware considerations. Now, I need to make this explicitly known to everyone that GIS your friend is using may not necessarily be the best one for you. Meaning that if you see a GIS application that is specific to, let's say, a tourist application, you cannot copy the application and hope that it's going to work for you and in terms of another application, let's say engineering applications. I cannot take a tourist information system GIS application and apply that in its entirety to fit an engineering GIS application. Some points you need to consider. Some of these applications are PC-based applications, meaning that it's in a standalone environment where a lot of the data is stored locally on the hard drive, while others might be in a mainframe or a server environment where data is shared across the internet or via a local network. Your friend also can be using a less expensive GIS. There are a number of free GIS that you can search online. Because it's less expensive, the processing is not as expensive as your commercial GIS. Now, your less expensive GIS application might be limited in terms of what the GIS analysis tools that's available. So, in one case, in a tourist information system, for example, that uses a GIS, they might be interested in looking at just showing pictures of a particular area in order to get tourists to come and experience the location, the tourist sites that is shown in GIS. While in a more extensive application, for example, the city tax office, they're going to have aerial imagery, they're going to have roads layer, they're going to have addresses. It's more extensive. So, in a nutshell, right decisions are required to choose the right GIS software based upon the money available. If you want to go the cheap way, there are free GIS software out there. If you want to go the commercial way, where there are a lot of opportunities in terms of data sets available, in terms of the applications out there that you can share data online, that's a better way to go. So it requires a lot of decisions up front. GIS is not a turnkey system, meaning that when you install the software, you cannot just install it and then start with a project and start working with an application. Installing the software is one thing, but actually a lot of your application depends upon the data. In order to process, use the tools available in your GIS software, you need to have the necessary data. Any GIS requires to be tailored to a specific requirement of the agency. So meaning that when you install your GIS software, you need to develop application together with the agency you're working with, or together with the clients that you're working with. They might be interested in a specific GIS application. For example, real estate office, they will be looking at coming up with a GIS application where they can see online or see on the computer via a map the real estate properties that they have for sale. And to do that, they will be required to collect the necessary data to do that. Once they collect the data, then they can use the GIS software to bring these things together. Basic issues need to be addressed before implementation are number of application packages. Apart from your GIS software, you need to recognize also there are other software that is available within the organizations that the clients and them would want to integrate into your GIS system. So what other application packages, for example, any Excel software or database or Access databases available that the client would want to integrate into the GIS system? What sort of transfer protocols? I want to transfer from one format to the other into the GIS system. Is it possible? That's a very important consideration. Can I transfer my Excel data into your GIS system, or vice versa? The structuring of your database also and the content need to be addressed. Is all of my data stored in a single database with only one table, or are there a number of tables that are linked together? And then lastly, you need to consider the organizational management. How is this data going to be shared? If at all, if it's going to be shared, how is it going to be shared within the organization? Or is it required that the data be shared via the internet? Another consideration we need to look at is building your database. It's an ongoing process. Your database is the most important component in your GIS. And you want to be protecting it by way of making sure there are backups, making sure that there are no virus that's going to corrupt your data. And you also want to make sure that your database is updated. All right. Remember, your data is going to be a snapshot of what you're collecting out in the real world. Also, you need to consider new applications require new data. So in order to build my database, in order to come up with new applications, I would be using some of the old data sets. I mean, there has not been any great changes, but if I need to do new things, I would have to collect new data sets in order to prepare these applications. Okay, this slide shows a simple yet informative way of connecting your hardware. And when I say hardware, I'm referring to your CPU, as shown here. Your CPU is very important in your GIS implementation or any computer application. I would urge all of you to get familiar with what are the contents of your CPU. If you have a desktop computer, I would suggest that you open if it's a one of those tower type desktop computers, open it up and have a look at where and see where the hard drive is located, where the RAM is located, and also the motherboard, and get a feel of what are the components inside your CPU. That is important because when you are implementing GIS, you need to have a basic understanding of what the computer consists of, and at the same time have a better appreciation of what's required in terms of the hardware in order to run the software, which is not just the GIS software, but also the operating system and any other application programs that you would want to integrate with your GIS system. So let's go back on this. On this slide, you are seeing the CPU connected on. It's connected to the standard your monitor and your keyboard and your mouse. And if you want to have it on a local network, you connect the CPU with a printer directly, or you can directly connect it also with your scanner or plotter or tape drive. Well, this is outdated, or any external drive that you might want to store your data and also your software. Now, it is important that you understand that you need to appreciate each one of these components of your computer has certain specifications, and when you're responding to any GIS proposal that is requiring a set of GIS application, you will be called upon to suggest what are the minimum specifications for your hardware in order to have your software running efficiently. You would also be asked to specify or give a minimum specification for the operating system and also any GIS software that you will be using in your GIS application. Let's look a bit more into detail what is involved in our GIS hardware in order to have an application that is efficiently run. Now, you need to look at three associated components with regard to your GIS hardware, and I refer to them as your physical components. All right, things that hardware that we can touch or feel. Okay. Hence the reason why I call it physical. Alright, we have three GIS hardware components identified on this slide. We have the GIS hardware associated with input, we have the GIS hardware associated with data management, and we have the GIS hardware associated with data output. Under your data input hardware, we are looking at one of the common methods of inputting your GIS data into your application is through a digitizing board. It takes your hard copy map and you would register it by inputting ground control, defining a coordinate system, and trace out the features on a special board that you need to purchase. You could also input your data by using a keyboard, by typing in coordinates, or any other way of inputting the data via inputting any text or numerical values through your keyboard. If you have one of those old tape reader, is another way of inputting, or if you have a thumb drive that's not listed here or shown, or an external drive, you could input your data in that form. You could also input your data from a data collector that surveyors or engineers would use out in the field when they're collecting data, and download. They would collect the data out in the field and then download it onto the computer when they get back in the evening in the office. The hardware components, physical components for the hardware for data management is obviously your PC. Collectively, you need your CPU, your monitor, and your keyboard that helps in order to manage data. You also want to consider that you might have a server sitting where all of the data is stored centrally. Alright, so you have one server or multiple servers, and connected to these servers, you're going to have client machines connected, doing their work and querying the data and storing it on the server. The third physical component of your GIS hardware is your output, and here we can output our data on a CD or DVD. We can output it on printers or plotters, or even thumb drives, external drives. We could also output it via the internet, create PDF files, BMP files, TIFF files, and email it to people who are wanting the final result. So there are many aspects in terms of the physical components of what the GIS hardware entails. So the questions addressed by GIS, and these are generic questions. I mean, your GIS system is going to answer multiple questions. So just want to give you an idea what type of questions GIS can answer. And of course, this depends upon the data that you have. One question, where are particular features found? What geographical patterns exist? Where have changes occurred over a given time period? Where do certain conditions apply? What will the spatial implication be if an organization takes action? And these are, I mean, as I said before, you can come up with multiple questions, and these questions are generated together with your clients. You will be developing GIS applications, not for yourselves, but actually for, if you are in a business of GIS, you will be preparing questions that need to be answered for the purposes of helping your client with their everyday work processing. Your database is the most valuable asset in a GIS. As I said before, you want to protect your database and make sure that you have multiple copies of it. You must also have an understanding that there need to be some sort of a cost recovery opportunities, meaning that if my data should be corrupted, all right, I want to be able to go back to previous versions and and work with that rather than starting from scratch. Sharing of data between agencies is another way of making sure that you have multiple copies, especially if you're going to have a network of servers. And on this network of servers, I can have multiple copies of my data set on the network. Should one of the servers go down, I can have there is a version of the copy of my data set in another server. Also, you need to consider the training and keeping the staff up to date with the new developments with the software, with the GIS software. This is a constant concern. So you have to make sure that people who are using the GIS developing applications are up to date with the training capabilities, and there are a number of opportunities for people to be trained, and one is what you're going through, for example. Others is that there are online training. The software developers have a lot of tutorials out there, webinars. You can actually purchase online training from the commercial vendors. So there are many opportunities. And also you need to understand that the training comes, a large majority of it comes from people being able to teach themselves. All right? Don't go and reinvent the wheel. It's very likely that what you're trying to do has already been done, and with the internet, you just search, and it's very likely that you're going to get help. Someone else has experienced the same problem, and that there are a number of solutions available. You are not alone in GIS business. 10, 15, 20 years ago, when GIS first came to the market, it was not very popular. Now it's becoming very, very popular across the different professions. It's an example from a text, shows you an example of a scenario where a place called Happy Valley, some of the questions that you will that is required for them to answer. Happy Valley has been established to help us ski resort managers improve the quality of the ski experience for visitors. The examples below are only a few of the situations in which asking a spatial question can help with the management of Happy Valley. One is where particular features found. 2, what geographical patterns exist. 3, where have changes occurred over a given time period. 4, where do certain conditions apply. 5, what will the spatial implications be if an organization takes certain actions. Another example of GIS application can be in finding a new home. In this flow chart, you see at the top of the flow chart, house hunting criteria identified, and there are a number of criteria. On the next level, in order to find a suitable house, that house must be close to a school, must live near a main road, would like to live close to an urban area, would like to live in an area with a low crime rate. We would collect the necessary data, so we prepare a map showing the school locations, a map showing the main roads, map showing location of urban centers, and then lastly a map showing the insurance zones as a, insurance zones would show where the crime rates as a measure of the crime rates. Using your GIS tools, you would come up with suitable maps, like maps showing the proximity to schools, maps showing the proximity to the main road, maps showing the proximity of the urban center. We would add some weights to these maps, and this is using your GIS software. And then we'll combine these, overlay them, and then come up with a final map where we can view the various houses, and if it's not acceptable, we then go back up into the flowchart and make some changes in terms of the criteria, in terms of the data sets collected. How are information systems created? Number one, it is created using people. Alright, your clients, the developers. These are the people who need to be on the same wavelength in terms of what they're trying to achieve, who are the people who's going to benefit from these applications. And together with, in order to do all of this, we need to have the hardware in place, which is what we spoke about in previous lectures. Also, we consider the type of operating system. Is it a Unix operating system? If it's an old operating system, which is DOS, or Windows, which is more the popular environment, Windows has a graphical interface. Then you would consider what type of GIS software that I'm going to use. Once you select the software, if it's a free software or the commercial software, both of them would require data sets. Determine what are the suitable data sets, and then start building your database system. Then I would consider what sort of statistical packages do I need, or any other application packages that need to be integrated with my GIS. Then you will want to introduce some text processing software. If I have some Word document or some other word processors that I want to integrate reports or the output from my GIS, export that into a Word document or some word processing software, I must be able to do that in form of creating the necessary reports in order to make better decisions. On this slide, you see a number of client PCs that are using various GIS software. Not just GIS software, you also have CAD packages that various client machines are actually doing different types of work. Now, typically, we would implement or develop GIS applications which are executed via computer network. The days where you develop your application on a standalone machines is non-existent again. The GIS implementation are typically done, and it is done in a way that data is shared across a network, and it is usually required that you have a DBMS, a database management system, that will help control the access to the data, who has read and write privileges in order to update the data or just view the data. And this is a very good diagram. It shows you where you have a DBMS here. Here is an example, Oracle, and connected on to the DBMS through, and the DBMS can be installed on one or many servers. in order to get access to data, these client machines are going to have the necessary login privileges or the read-write privileges in their account. On this diagram, you see another configuration, but more explicitly you are seeing the other peripherals connected onto a computer, and this computer can be looked upon as being, let's say, it's a server or a high-end PC that is connected on through the internet or some intranet within an organization. But connected onto the server, you have a scanner, you have a digitizing board with a digitizing puck. You also have the ability to store data, share that data on via the server, where all of these clients here can have access to the relevant data set. Of course, going through the necessary protocol of who has the read-write privileges. It's also connected onto a printer and a plotter. The GIS expert creates, these are some of the applications what GIS people are involved in. You can create a cadastral systems. Cadastral systems are referred to land and property ownership. You can create a forest management system looking at the forest services. They want to be able to manage the state lands and manage the vegetation on the state lands. I want to classify the data in terms of deciduous, evergreen, or I want to be able to look at any easements or public right-of-ways within the forest services, or I want to create a site analysis system where for example, I'm looking at identifying suitable sites for putting a landfill, or suitable sites for putting a new mall or new school, things like that. Another possible application is taxation systems, where the revenue office might want to manage the taxes being collected within their county and make sure that all of the taxes are collected every year. Another possible application is watershed management. I'm looking at where do I need to position dams in order to create a water source for a certain area, or create a dam to generate electricity. Another application is in environmental monitoring systems. This is a very popular area in GIS, being able to, since we are very concerned about the environment and future generations, we want to be able to look at the greenhouse effect, or it is said that the ozone hole is getting larger and larger. Well, that's an environmental monitoring system. And the list goes on and on, like archaeological information system. You can have a business information system. You can have crime analysis, and the list goes on and on. On this slide, it gives you a general idea of the schematics of GIS, what it involves, and it involves the users, and these users can be end users and also your clients. So your client comes in, talks with you, and says, okay, these are the specifications for my project. I want you to develop a GIS, and in this GIS, I want some results. All right, you would incorporate all of your discussion with your client, will ultimately be your users, and use the relevant GIS software tools together with the data. Now, the data is very, very important. Now, it is more expensive to get data when you compare purchasing data as opposed to purchasing the software and the hardware. The data sets are more expensive. Okay, especially where you're going to have to go out in the field. If you have to go out in the field to collect data, time is money. So the longer time you spend out in the field, more costly it's going to be to get the necessary data and the level of accuracy that you're looking at. Now, so your GIS, the schematics of this diagram, it shows the users. You have your GIS system, and the GIS system produces some results. Now, your database is some abstraction of the real world. And you're not going to go out there to collect all possible data sets. You're going to collect data and store it in databases. You're going to collect the data that is relevant to your GIS application, and also at the same time that is you collect data that is critical to your intended GIS application. Now the next section in Lecture 3 is Information System Architecture. There are 3 types of architectures listed there. It's independent functional process. Second, mainframe or central approach. Third, network distributed processing environment. We're going to look at each one of them individually. We're going to look at the characteristics, then we're going to look at the advantages and disadvantages of them. Independent functional processes. This is a setup where your GIS is actually on a single computer, not connected onto any network or not connected onto the internet. And all of your software is stored locally on the hard drive. The data is available on the hard drive. You do your application development within the limits of or the confines of that particular computer. The description of it is independent processes, decentralized operation and management, decentralized application development, and it's only departmental finance. So within a department, you might have a few computers that is not sharing data among themselves. Each, in order to use data, you have to copy it and from one computer to the other. The department is in charge of financing. In terms of financing, upgrading the hardware and software, and because of that, it's limited in terms of the amount of money that is given in terms of their budget per year, or however they are given their money. Anyway, there are a number of advantages. The advantages is potential for integrated graphic and database application. I have more flexibility in doing whatever I want in terms of developing my GIS application, since no one is in control or limiting my exposure to developing whatever I want using that single computer. Acquisition of hardware and software to meet specific functional requirements. If I want and I get the necessary approval, or I have the money for it, I can buy a scanner, I can buy a GPS, and plug it into my standalone computer and it'll work. No problem whatsoever. It's moderate cost. All right, but remember, you can look at this GIS implementation architecture as being a GIS being developed within a vacuum. All right, no one else knows about it apart from the people that are within the department. On this slide is you would see a workstation PC connected onto a printer or plotter. Years ago, when GIS first came into the market, this was the ultimate installation of your GIS system. You have to remember, during that would have been 10 or 20 years ago, when the internet was not available. Setting up a local network within an office environment or within an organization was the ultimate networking capability. But what you're seeing here is a simple GIS implementation that you might want to implement especially if you are asked by your employers to show them what GIS can do. So what you want to do is keep it simple and do a standalone GIS application. Develop the application and present it to your to the people who make the decisions, and if they love what they see, then you can start expanding it out to include servers and softwares, and being able to share data sets and processing capabilities. Disadvantages, it's obvious. Number one is limited data sharing. If I want to get data from, let's say I work for the engineering department, and I want to get land surveying data from the surveying department, I cannot share. It's not available. All right, my data is not accessible to them, and their data is not accessible to me. Limited coordination. As I said before, I can put whatever I want on that computer. All right, and because I'm doing that, it might be that I might install a wrong program and corrupt what data sets that I have on the hard drive. Extreme difficulty in maintaining data standards, meaning that I can collect data whatever specification. All right, there are no rules and regulations I need to follow. Limited hardware capacity. I will be limited to what the single computer has in terms of the storage space, in terms of the RAM that's available, and also if I need to upgrade, I have that limit in terms of is my computer upgradable. Difficulty in data communication. My computer, I cannot log on to the internet, and it's because it's not part of the networking infrastructure. Complexity of operation and management is very complex. I mean, you're doing things like installing, any types of software, the free software, the commercial software, and there is no management of it. So that's a big disadvantage. The other GIS architecture, which is a much better architecture compared to your standalone architecture we spoke about last slide, is your mainframe or central approach. That is similar to what we call it's a client-server environment, where we have one server and the clients can be multiple PCs that is communicating with your server. It's a centralized approach, centralized processing, centralized management, central application development, and also joint financing. Very big. A lot of good things what the mainframe or central approach has to offer. Our joint financing, you can look at it where we have multiple departments. They all share a common server in terms of the financing of the hardware of that server, the financing of the software of that server. The advantages I can have is, number one, data sharing. We can share now among the different departments. The ability to maintain data standards. Every department will follow specific data standards. For example, everyone's going to collect data at a scale of 1 into 500. And the pixel resolutions for satellite imagery is going to be let's say 1 meter by 1 meter. There's a lot of another advantage, flexible hardware capacity, meaning that we can have a server where we have multiple hard drives, and we would share the cost accordingly if we want to upgrade. There is also another advantage, access to a range of system software. We can put multiple software once it's approved by the IT people who are managing and the server and the network. They will be controlling the type of software that we're going to put on the server. Uncomplicated data communication. We can share data across share data from the server within the departments, various departments. good technical support staff. We have IT people who are managing the network, managing the server, so we have competencies on board. And lastly, another last advantage, less difficult operation and management. We have people who are managing it, and there is competent people who are actually making sure that everything works. This is an example of what a client-server GIS implementation looks like. It's a simple one where we have one client connected onto one server, and this server is connected onto some external drive or some other system that has more storage space. Now, this is the preferred method in terms of implementing the next level of from a standalone to what's the next level is going to be a client-server environment. One server, one client, or one or more clients. Why? Because the server is going to have your DBMS, the database management systems, that's going to control who has access to the data. It's going to control the security, maintain data integrity. So it is a preferred method in terms of if I want to now share my data on this server via the internet. I'm going to install some firewall capabilities, and I'm going to install probably a GIS server software where the data is stored on this server, and a set of GIS services will be made available to the World Wide Web, so where people can view the data. And if you want it open such that people can, or users can download it, so be it. You can have that flexibility. Disadvantage: limited ability to integrate graphic and database requirement. It is limited. For example, if we have one server and that server has an operating system that is Unix based, we cannot integrate from, let's say, data from another operating system. There need to be, there need to be some seamless integration when we start talking about different operating systems. Another disadvantage: independent graphic processors required. It all depends what we're going to do. Let's say our surveying department, they are using CAD systems, and our planning division, they are using a different package that requires different graphic processors. Then we need to have the server capable of doing these things. Low level of department and control. One department cannot dictate what the entire organization is going to do. All right. For us to make any changes, it has to be supported by all departments. High level of intergovernment cooperation required. If we are looking at a server and we're talking about government investing in a single server where all the departments or ministries are using this particular server, we need to get cooperation between the departments. High cost. Yes, it can be very costly. Servers are very costly, and in terms of upgrading the components in the server can be very costly. And if it means one department doing high-end processing, it means that all the department will have to chip in, put money into the pot, to upgrade the server, even though one department is going to use it. Tendency to purchase too much excess capacity, and that's along the lines where departments are overbuying the components of what the server has in terms of what they're going to do with the server. So they tend to buy things like more storage space, and they don't actually use all of the storage space. The last architecture, which is the recommended architecture, is what we call network distributed processing environment. Instead of one server, we have multiple servers. Okay, so it's an improvement on the single client server environment that we talked about previously. Network distributed, we have multiple servers, and each server is going to have copies of the data, and the software is also shared across the different servers. We have coordinated operations and management, coordinated application development, good technical support, joint and departmental finances. I mean, most servers we have, it's going to be more expensive, but it's going to be shared across different departments and organizations. Advantages, number one is we can share across the network. We also have the ability to maintain your data standards. We have also the potential for integrated graphic and attribute applications. One server could be a Unix environment, the other is a Windows environment. So that's great. We can now, it becomes much more flexible in terms of what we want to achieve. Moderate to high-level department control. We have also another advantage, flexible hardware capacity, access to a range of system software. One server going to have a set of software, another server not going to duplicate the software, but you're going to have much more software, more flexibility in that regard. Access to good technical support staff, moderate costs, and then lastly, phase growth. For example, what I mean by phase growth is I can have 2 servers, and that lasts, the development, let's say for 2 servers lasted around 5 years, and another 5 years we add 3 or 4 more servers. So phase 1 was just 2 servers, phase 2 we have 3 servers, so altogether we have 5 servers. Phase 3 we add 5 more, so and that's what we talk about phase growth. On this slide, you see schematic of what a multiple server client environment look like. As we call it in the previous slides, our network distributed architecture, where you see a number of servers. So you see 2 servers here, and it's going through a set of hubs, and it's going to give access to various client PCs. In the diagram, you see desktop computer, different organization. This can be one organization that has its own database, and another organization here that has a database that is stored, that's connected onto this particular Oracle server. And another server here is going to have probably ArcInfo, GIS software, or QGIS. So this is what ideal and ultimate GIS implementation when we start talking about a network distributed environment where we have multiple servers. Should this server go down, for example, there's going to be copies of the data shared. We can program it such that there are multiple copies on different servers. So if this goes down, users who are using the data could get access to the other server and continue working with what they have been doing. This concludes our discussion on GIS network architecture. I would strongly urge you to go back and download the PowerPoint note presentation, go over the material, make sure that you understand it, and then we'll continue with our next discussion about data in GIS.